So for Chem 100 and Exam 9, this is Chapter 18 from your textbook on redox reactions and electrochemistry. We've already done a review the last time we met using Cengage homework, which had a few challenging problems. Now we're going to work from the review document that's located in Blackboard and pick out. There'll be a considerable amount of overlap, but practice, as they say, makes perfect. So what I'm going to do first is share that review document. It's located in Blackboard. And this is it right here, I believe. There we go. So in fact, I think I can make that even bigger. Yeah, that's good. Okay. So I picked out some problems, but I think I may, on my way to these problems that I've marked out on my hard copy, I may stop occasionally and pick up an odd one or two that I had not marked out. So let me scroll down to, I want to start off slow. Let's start off with oxidation states. An oxidation state of an element, either a free element or an element in a compound, is a way of electron bookkeeping. We just want to keep track of the electrons. Where are they moving? And it's a method that's developed and become very useful for oxidation reduction type reactions. So if we take this first one and we say, what's the oxidation state of sulfur in this molecule? Correct? K2SO3. That's potassium sulfite. Now there are two approaches that we can take. Since the molecule is not large, we can take the whole thing together, and all of the oxidation states total for every atom in that molecule must add up to 0. Give me a second. Okay. That cat that was trying to dig into my plastic bag with catnip in it. So I pulled out one of the toys and throw it to her so she can, and she's loving it. Okay, let's get back to this problem. So the question is, what's the oxidation state of this atom in that compound? So if we do the whole thing together, we know that by definition, all alkali metals are +1. And oxygen is taken as -2. So the total of oxygens is -6. 3 times 2, and 2 times 1 is that. So together we have -4. That -4 has to be balanced by equal magnitude, opposite charge from the sulfur. So sulfur has to be +4 in order for the molecule to be neutral. So that's why the answer here is +4. But suppose you had a large molecule and it had this polyatomic ion in it. you only need to deal with that polyatomic. As long as you know the charge on the polyatomic, then adding up these oxidation states must be 2-. So again, oxygen is -2 times 3 is -6. But we need to keep 2 of those negative charges for the whole molecule. So really, you only have to balance a -4. So +4 is assigned to sulfur. So you get the same answer either way. All right. That was number 4. Let's see. Well, I don't have any of these marked, but we're going to practice. Probably the most difficult oxidation state to determine in any molecule is carbon, especially if carbon is located in an organic molecule. Now, carbon dioxide is not an organic molecule, right? But methane is organic. Any fatty acids are organic. And it takes just a slight tweak to know how to deal with the carbons in those atoms. This one is simple. Carbon dioxide we know that oxygen is taken as -2, so that's -4 total. This carbon has to be +4. Right. That's the only possible answer for this one. If we took carbon in methane, then hydrogens are taken as +1. And that means +4 here, -4. So these two compounds represent the extremes in oxidation state for carbon. Carbon can go from +4 to -4, and anything in between, right? Be +4, +3, +2, +1, 0, -1, -2, -3, -4. Be all of those possibilities depending on the compound, where it's located. We'll come back to carbon probably in a few minutes. But let's move on and try some different elements. Perhaps ones that are transition metals, like MnO4- for number 8. Right. So the total of the oxidation states must add up to a -1. So this oxygen is -2 times 4 is -8, but we need to hold one of those negatives for that charge. That means we only have to balance a -7. So this manganese is a +7. Right there. Okay. How about let's move down some more. Okay, here's a trick question. What's the oxidation state of O2? Oxygen in O2. I had several cats interested in that catnip now, so I had to give them the other toy. Any element in its standard state is automatically oxidation state 0. Sometimes it's helpful to think of oxidation states as what would that element be? What would the charge on that element be if the compound were ionic? It may not be ionic, it might be covalent. But like I said before, this method is a bookkeeping scheme for tracking electron movements. So we just have to establish rules and follow them. Any element in its standard state is an oxidation number or an oxidation state of 0. So any of the diatomic gases would be candidates for a 0 oxidation state, like hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. Those are all diatomics. Sulfur in its most common state is S8. 8 sulfur atoms together. Its oxidation state would be 0 also. Okay. How about this one, number 15? And remember when we were trying to write and name compounds earlier, we were already doing some of this, right? We were saying magnesium is an alkaline earth, so it's always +2. Well, that's the same rule that goes with oxidation states. It's a +2, right? And this polyatomic is a -3. That's why the 3 comes over here and the 2 goes over there. But when we're doing oxidation states for individual atoms, that can be useful, right? This is already, we know that's +2, so it's +6 total. And this one, there she is. Let's see. Okay. I started without you. And we've really only gone up through practicing determine oxidation states. So in this one we have, which is number 15 in your review document, is +6 total for those magnesiums. Now, how many phosphorus do we have? Well, we've got 2 of them. That's the question. What's the phosphorus oxidation state? So we need to concentrate on that oxygen. This oxygen is -2. How many of them are there? Actually, there are 8. 2 times 4 is 8. So 8 times that is -16. Right? These charges up here, this charge doesn't matter. If you're using the method where you're going for a neutral compound, you just take the individual atoms. So that's -16. That's +6. So together, we have a -10. All right? So the phosphorus has to balance with a +10. But there are 2 of them, correct? So 2 of them means +5 for each one. And that's why the answer is +5. Here's a case where it might be simpler to just break out the polyatomic ion and say PO4 3-. Now the total has to add up to 3-. Okay, and it doesn't matter how many there are. It only matters the polyatomic ion. So with 4 times a -2, we have -8. Subtract 3 is a minus, well, add 3 minuses. We only need to have -5 balance because these 3 minuses were extracted from that. So now this has to be +5. So there we've answered the question, I think, easier if you have a polyatomic ion involved and the question concerns one of the atoms in that polyatomic ion. Okay, how about 16? We have this compound, CuSO3. Okay, we can go in and do every element in there. Oxygen is -2, so that's -6. Right? The question is, what's copper? Well, first of all, what's sulfur? Right? Well, sulfur is in the oxygen group, so it's usually taken as 2-. But sulfur can have multiple different oxidation states. So let's see what happens if we make it 2-. If we make it 2- or -2, and that's -2 here, and that makes -8. So that makes copper +8. But that doesn't make any sense, because if you look at your periodic chart, that's not a choice. Right? So that method's not going to work, because sulfur is obviously not -2. So here's what we do. We know that sulfite is a polyatomic ion, and it has a -2 charge. So to balance that -2 charge, copper has to be a +2. That's the oxidation state of copper. So I'm curious, what is the oxidation state of sulfur? If we pull it out like this, okay, 2-, then this is -6 total for that oxygen. We have to hold out 2 minuses, so we only need to balance for -4. Sulfur is +4. That's why our previous example didn't work, because we were using the wrong oxidation state for sulfur. So in this case, balancing these two charges is a more efficient approach. Doesn't matter what sulfur is. We know that the charge on that polyatomic is -2, so copper has to be +2. Okay, I think we've done this one before. Dichromate ion. We'll do it again. Okay, so what's the oxidation state of chromium? Well, we know oxygen is -2 times 7 is -14. Hold 2 of them out for that minus. -12 is all we have to balance. So -12 needs a +12 here, but you have 2 of them. So chromium is +6. Right there. Okay. All right. Let's see. Well, let's look at 20. We have this ammonium bromide. Okay. Well, we know that the polyatomic ammonium is +1, right? So that means bromine has to be -1. Also, barring any other complications, bromine will always be -1 because it's a halogen. But bromine can be other oxidation states. It depends on what it's bound to. What if we say, let me see if I can think of one. No, nothing comes to mind. Okay. So let's look at, let's see. How about these three together? 21, 22, 23. They're all based on the same compound. Okay. For 21, we want to know oxidation state of carbon. For 22, we want the oxidation state of iron. And 23, we want the oxidation state of oxygen. Okay. Based upon this compound. Okay. The first one I would go for is iron, simply because we know the charge on CO3. Right? The total charge on CO3 is -2. Right? So -2 times 3 is -6, balanced with +6 over here. That means each iron has to be +3. Right? So we got that one. Now we'll go inside the polyatomic ion, CO3 2-. And oxygen, we have to take oxygen as -2. We really don't have any choice in this case. So -2 says here. But how about carbon? Well, let's see. 3 times -2 is -6. We have to hold 2 out for that charge. So -4 has to be balanced with +4. So that's for carbon, +4. +4 for carbon, +3 for iron, and -2. -2 for oxygen. Okay, let me see here. All right, we did earlier in the video, I did methane and carbon dioxide, so they're already done. The carbon dioxide is +4, methane carbon is -4. Okay. That nails down both extremes. Carbon can go from +4 to -4. That's it. Anything in between, depending on the compound. All right. So I don't think I have an example. So let me try to make something up for carbon. Let's say we have like that. And then we'll put see, this is going to have hydrogen, and this one like that. Okay, that'll work. All right, so what are the oxidation states on each one of these carbons? Well, the thing about carbon is we have to take individual carbons in this molecule separate. So in other words, we have to add up everything that's attached to that carbon has to add up to 0 because there's no charge there. All right, so we do each carbon separately. If a carbon is attached to another carbon, then the contribution of that other carbon is 0. It has no effect on the carbon of interest. And so if we were looking at this carbon, then we say that has nothing to do with it. It has to balance against this nitrogen. And nitrogens are taken as -3. Right? If you move from right to left, right? Let me see. Let me get my picture back up here. If you move from right to left, you have fluorine is -1, oxygen -2, nitrogen -3. So in this case, we would say that's -3. That means this has to be +3. Right? Because that carbon has no effect. How about this one? We got 2 carbons here, right? So they don't count, but this oxygen is -2, so this carbon has to be a +2. Here we got 2 carbons on either side, right? They don't count, but this hydrogen is +1. That means this carbon has to be -1 oxidation state. And on this one, that carbon doesn't count, but this is a -1, that's a -1, this is a +1. So those two cancel each other. That means this one only has to balance +1. So in this molecule, you got a -1, +3, +2, +1. You got a whole bunch of different ones. What if instead of that nitrogen, we had turn this end into a carboxylic acid? Right? In that case, this one has no contribution. That one's a -2. This one's a -2. This one is a +4. And notice I didn't go out all the way to hydrogen. I just stay with the bonds on that carbon. That's how we do organic molecules, determining the oxidation state of carbon in organics. Okay. Let's see, my periodic table's come undone. Let's set it aside. All right, so let's get back to the document here. How about 28? In reacting, metal atoms, and what we're saying here is individual neutral atoms of metals. What do they characteristically do when they react? Metals have a tendency to give up electrons, right? They tend to lose electrons. They tend to be oxidized. So, do they become anions? No, not if they lose electrons. Anions are negative, right? So they do lose electrons. That's true. Do they decrease in oxidation state? No, they increase. They go from 0 to some positive value. That's a decrease. In other words, the more positive you get, you decrease the number. You increase the number. So decreasing oxidation state is wrong. Can't be. They form covalent bonds? Generally speaking, no. Now, there are situations, which is beyond this course, where some metal atoms can form something associated with covalent bonding. But it's, like I said, it's beyond the scope of this course. So for now, you just assume that metal atoms always transfer their electrons completely to something else, a non-metal. They don't form covalent bonds. So the only answer to this one is B. They lose electrons. Now, for non-metal elements, they can go either way. They generally accept electrons. They want to be reduced. But when they're in association with each other, like non-metal and non-metal, they form covalent bonds, then you got to make a choice, you know. And generally, the more electronegative atom accepts electrons and becomes more negative in its oxidation state. And the less electronegative one assumes the positive oxidation state, which is the case with carbon dioxide. Right? Which one's more electronegative? The oxygen. So the oxygen gets the negative, and the carbon gets the positive. Right? And like I said before, this is a bookkeeping scheme. That doesn't mean carbon has a charge. That just means that's how we're tracking electrons. All right. Well, let's see. How about, well, while we're here, we'll just do number 29. All right, for this reaction, we've got 2 potassiums and copper 2 chloride yields potassium chloride plus copper. Okay. Now, we know this is an oxidation reduction reaction, right? Because one of the clues is potassium is an element here, it's in a compound here. That only happens with transfer of electrons. Copper's in a compound here, it ends up as an element here. That also is an indicator of transfer of electrons. So this would be an oxidation state of 0. This would be 0. Chlorine is -1. Potassium is +1. It's an alkaline metal. These chlorines are -1 each, so that's -2. That makes this one a +2. So now we know all our oxidation states, and we can say what happens. Right? So what happens to potassium? Potassium goes from a 0 to a +1. It is oxidized. It loses electrons. Chlorine doesn't change. Copper does change. Copper goes from a +2 to a 0. It gains 2 electrons for each copper. So it is reduced. Now let's see which one of the answers, which statement is true. Copper is reduced. That's true. Nothing happens to chlorine. That's false. Potassium, nothing happens to potassium. Yes, potassium is oxidized. It's not reduced. That's false. And copper can't be reduced and oxidized. So D is false. A is true. Chlorine is oxidized. Nothing happens to chlorine. So the only one out of those is true is copper is reduced. Okay. Let's see. Well, there's a whole bunch of them that I kind of skipped over. There's repetition there. Let's move on to 51. 51, right there. Answer the following questions. Okay, now we're going to step it up. Notice that in this proposed reaction, we have dichromate ion and iodide ion yield chromium 3 plus and iodine element. That can't be the whole story because there's oxygen over here and there's no oxygen over there. So one of the clues is determine the coefficient of water in the balanced equation. Right? And remember, water is one way that we balance oxygens. Well, that's the only way that we've learned to balance oxygens. So we need to balance this equation. All right, so 51, let's put it up here. We're going to balance this equation. Cr2O7 minus 2. That's aqueous. Well, they're all aqueous except for iodide. It's solid. But in this case, well, we will. Let's just go ahead and be consistent. There we go. And that one's aqueous. And we're going to have that one and this one. Solid. Okay. So what's the first thing we have to do? We have to know oxidation states so that we know which reactants are reduced and which are oxidized. Then we can split the equations in two. So this one we did before, but we'll do it again. So it's minus 2 here, so that's minus 14 total. We have to hold out 2, so it's minus 12. That has to be balanced. So that's plus 12 here. That's plus 6. Okay? So that's going to get cluttered. Let's just erase those things. There we go. Well, this oxygen is minus 2. Iodide, that one's already minus 1. It's done for us. That one's 3 plus. It's a single atom with a charge. That's its oxidation state. And this one is 0. Okay? Now, which one's oxidized? Which one loses electrons? This one. Iodide goes from a minus to a 0. So it loses loss of 1 electron per iodide. And this one is oxidized. Gain. Excuse me. It's reduced by gain 3 electrons per chromium. Okay. Now let's split our reactions out. I like to do oxidation first. So the oxidized one has lost electrons. Iodide yields iodine. Okay? And the reduction part is dichromate. Okay? Plus 6 here. I'm going to keep that. And it becomes chromium 3 plus. Okay. We got our oxidation and reduction reactions are separated now. Now what do? We balance the elements, everything except oxygen and hydrogen. So we need 2 iodides over here. And we need 2 chromiums over here. Right? 2 and 2. So that's done. Now we need to, well, actually at this point we can either do electrons or we can do oxygens. I think the method I gave you in the lecture was do the oxygens first, so we'll stay consistent. We've got 7 oxygens here. We need 7 waters to give us 7 oxygens. Now we have 14 hydrogens. There we go. So the hydrogens are balanced, the oxygens are balanced, chromiums are balanced. Now let's put in the electrons. This one was a loss of 1 electron per iodine. So how many electrons were actually lost? And besides, and in addition, which side of the equation do they go on? If this lost electrons, the electrons have to end up over here. 2 electrons, because it's 1 for every iodide. How about this one? This is 3 electrons for each chromium that we have to add. Right? So 3 times 2 is 6. 6 electrons were actually added. Okay, now we have to make the electrons balance between the 2. This is 6, that's 2, so we need to multiply this one by 3. Okay, this becomes 6, and this becomes 3. Okay, now we can add them together. Let's see if we can cancel something. I forgot, this one's 6. There we go. These electrons can cancel. Nothing else can cancel. So we're going to have dichromate plus 6 iodides plus 14 hydrogens yields 2 chromium 3 plus 3 iodines plus 7 water. Okay, now let's see, can we reduce this any further? Well, no, that's 1. We can't make it any smaller than that. So that's it. Now, what's the coefficient for water? What's the coefficient for water? It's 7. Right there. And you can't know that unless you balance the equation by this method. You can't just eyeball it and say, oh, I know it's 7. Doesn't work that way because, first of all, there's no water up here to begin with. So where does the water come from? The water has to come from this balancing process. Okay? That was 51. And the only way you can get good at this is to work a lot of them. Work as many of these problems as you can until you're bored stiff. If you're not bored, you haven't worked enough of them. All right. I've got, did I mark off 52 also? Yes, 52. For this reaction, 52. For the reaction of sodium bromide with chlorine gas, sodium bromide with chlorine gas yields what? sodium chloride and bromine. Sodium chloride plus bromine. The appropriate half reactions are what? Well, notice there's no oxygen here. So we're not going to have to worry with adding water. Right? We just need to separate them into oxidation and reduction. These are both zero. Right? Sodium's +1. This is -1, +1, -1. So this is a fairly simple one. All right. So which is oxidized and which is reduced? Oxidation is loss. So this bromine minus loses an electron to there. All right, there we go. Reduction is the other one. Chlorine yields chloride. Okay? See, even though we have these as compounds here and here, sodium is a spectator. So you can ignore sodium. It doesn't participate in the reaction. So if this is oxidation and that's reduction, then we need to balance the number here and here. Since there's no oxygen to balance, we go straight to electrons. So this one had to lose 1 electron each, which means 2 electrons. And this one had to gain 1 electron each, which is 2 electrons, right? Because we have 2 chlorines. Okay, so we could put those back together now and have a balanced equation. But the question is, what are the oxidation reduction half reactions? That's what these are called, half reactions. Well, let's see. The oxidized one has 2 bromides, yields bromine. So let's see, oxidation. There you go, 2 bromides equals bromine plus 2 electrons. Let's see if the reduction fits. Then we have a chlorine atom molecule. 2. There it is. It's B. Let's see if I can do this. There we go. B is the one that fits. Okay, that was fairly simple. All right. Okay, that was 52. Let's see. I got 53 marked also. So the balanced equation for the following redox, in the balanced equation, what's the sum of the coefficients? Sometimes they say that. It's just a method. Excuse me. A mess. There we go. 53. So we have this one, Fe3 plus iodide yields Fe2 plus that. Okay? So oxidation states. It's easy. Charge, 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 0. Okay? So the oxidation equation is which one lost electrons? The iodide. Okay? And which one was reduced? That was the iron. So we had to add an electron here, right, to give you 2 plus there. And here we had to, well, we got to balance these, right, 2 there. So this is 1 electron lost for each, but there are two of them. Right? So now that means this one has to be multiplied by 2. So it's 2 Fe 3 plus 2 electrons yields 2 Fe 2 plus. Okay. Now the electrons cancel. And we add them back together. So we've got 2 Fe3 plus 2 iodides yields 2 Fe2 plus I2. Okay? So what's the sum of the coefficients? 2, 4, 6, and don't forget that one, 7. Just because there's no 1 there doesn't mean it's not there. If you have that there, that's at least one of them. So the coefficient's 7. Right there. Okay? Let's see. Let's see, I have several marked off. Let's go to 55. Okay. $55. For the redox reaction, it just tells you the redox reaction. We know this is similar to the one we just did. Except now we're substituting. Actually, it's the one we just did. 2 changes. We changed iodide to chloride, and we flipped the reaction in reverse. Like that. Okay, which of the following are the correct half reaction? We should be able to knock this one out pretty quick. This one is oxidized. This one is reduced. It goes from 0 to -1. Okay, we need 2 of those. We only need 1 of those. So this one has to lose an electron for each iron. This one has to gain an electron for each chlorine, which means you need 2 of them. So to balance them, we need 2 of these, 2, 2, 2. Electrons cancel. Now we can add them back together. So which of the following are the correct half reactions? Well, we need Fe2 yields 2 Fe2s, 2, 3, there. This is one of them, 4. And the other one is add 2 electrons, so it's 1 and 4. Those are the correct half reactions. It doesn't say which is which, but you can tell from which side the electrons are on, which one's oxidation and which one's reduction. All right. So let's move down to 57. Now we've got, if we're going to balance this one in acidic solution, all right, we've got oxygen, so we're going to have to go the whole 9 yards on this one. All right, 57. Our starting reaction is What is this? The chloric, no, excuse me, chlorate polyatomic ion. That's chlorate. Chlorite would be ClO2 minus. Hypochlorite would be ClO minus. Perchlorate would be ClO4 minus. This is chlorate. Plus iron, 2 plus, yields chlorine plus, well, chloride, I should say, plus this one, 3 plus. Okay, what's the oxidation? Well, we got to do that. That's good. That's charge, charge, charge. We have to do this one. So this would be -6 for the oxygens. Hold out 1, +5 for the chlorine. So +5 to -1 is reduction. So the oxidation must be iron. Right, so we got iron, 2 plus, yield, iron, 3 plus. And reduction is this one, ClO3 minus, that's 5. And then yields chloride. Okay, those are balanced. These are balanced. Now let's balance the oxygens. We need 3 oxygens. Now we got to balance 6 hydrogens. Okay. Now we'll put the electrons in. This one had to lose 1 electron. This one had to gain. What's +5 to -1? How many electrons you have to add? Well, 5 electrons would make it 0, and then 1 more. Okay? So now we need 6 electrons up here. 6, 6, 6. Now we can cancel those and add these back together. If that's what we were supposed to do, is it? Coefficient of iron, 2 plus. Okay. Well, we know that right now. Right? Add them back together. It's not going to change the coefficient. Iron is a 6. Right? We only got 1 there, 3 there, 6 there. So we can't reduce it any further because that one is 1. So that means iron 2 plus is the number 6 coefficient. Right? We don't want to waste any time taking a test, so we can answer the question right there. We don't have to add them together. That was 57. All right. Let's see. I've got, what else do I have marked off here? $60. All right. 60 asks, in a car battery, which of the following is the electrolyte? So what do we mean by car battery? We mean lead acid storage battery. So what's the electrolyte? What do we mean by electrolyte? Well, the electrolyte is the fluid, the liquid part that surrounds the electrodes. In the lead acid battery, the same electrolyte surrounds both electrodes. That's why you don't need any partition between the half cells, because they share the same electrolyte. So what is the electrolyte? The electrolyte is sulfuric acid. and it's fairly concentrated. In fact, I can remember older type batteries that had to be vented because when you go through a discharge and a recharge cycle, you tend to generate hydrogen gas. And it's not by the reactions, the oxidation reduction reactions for the battery. This is a side reaction. And what happens is you convert, as a side reaction, you convert water into hydrogen gas and oxygen gas. Right? So that would be 2 here and 2 there. You electrolyze water, right? You produce that hydrogen gas, and if it builds up in your battery, it'll explode. So they're vented. But what happens is, over time, with the charge and recharge cycles, you lose water from your battery. And occasionally, you have to, in the older batteries, you had to add a little bit of distilled water back into it to make up the difference. And that's all you had to do then was just visually look at inside the cap, pull the cap off, add water, distilled water only, and until it reaches up above the plates, and then put the plug back in it. But sometimes you can lose sulfuric acid also. Remember what happens. Both half reactions produce what product? Lead 2 sulfate. Right? That's produced at both the cathode and the anode. And after so many charge and discharge and recharge cycles, you build up this lead sulfate on the surface of the electrodes, and then now they're not, you can't recharge anymore, and it's said to be, then your battery is sulfated out. But on the journey to that point, you lose sulfate from this, right? And consequently, you lose hydrogen also. So if that happens, then if you keep adding water, you dilute your sulfuric acid until it becomes so dilute that your battery won't work anymore. So what the full service stations would have this device called a hydrometer. What the hydrometer did was it would measure the density of the electrolyte. And if the density decreased below a certain amount, then you had to add sulfuric acid back to it, because the density of sulfuric acid aqueous solutions increases with concentration. So the more sulfuric acid, the more dense it is. And you use that hydrometer, and it was calibrated. I just had red zones and green zones and yellow zones on the thing. Didn't actually give you numbers, but the principle was the same as a hydrometer. And it would give you an indication of whether your battery had too much water in it, not enough sulfuric acid. And then the technician would bring out some concentrated sulfuric acid and add it back in. That's not something that you want to handle. They wear the gloves and garb and everything. Nowadays, lead acid batteries are, they're not completely sealed, but they're manufactured in such a way that they don't spill, and they may have a gel in there to keep the sulfuric acid from spilling out. And they don't tend to lose well, they can still become sulfated out. But they're what I would classify as low maintenance. So, all of that to answer one question. The electrolyte is sulfuric acid. All right. Let's see. 61. Okay, we're still talking about the lead acid battery. The lead storage battery, they say. So where is PbO2 found? All right. So what you need to do is say, all right, PbO2 is one of the electrodes. 61. One of the electrodes, and it yields PbSO4. Right? Both electrodes yield PbSO4. So, what is the oxidation state here? Well, if this is 2 minus, that has to be plus 2. And if this is minus 2, minus 4, this is plus 4. So what has happened? PbO2 has been reduced. And 2 electrons. That balances this plus 4 and gives you a plus 2. Okay? So, what happens? What do we call the electrode at which reduction takes place? It's called the cathode. That's the site of reduction. That's definition. That's all it is. So that's why the answer to this one is A. All right. How about 65? We talked a little bit about this one last time because I couldn't remember the guy's name. Hall. The Hall process reduces aluminum in its state in ore. 65. Right. And what's the ore called? We didn't mention that before. Aluminum ore is called bauxite. And there are places in the world where it's especially concentrated. I mean, aluminum is everywhere. But if you're going to make the pure metal from the ore, you want to have as concentrated a feedstock as possible. And they take bauxite and they purify it at the mine to a certain level so that it's mostly aluminum oxide. And then they ship it off. It's commonly found in tropical regions because what happens is the soils get lots of water year-round, and it leaches everything else out. Anything that's soluble goes like that. Aluminum oxide is not particularly soluble, so it's left behind. Iron oxide also. But you look for these sites where aluminum oxide is a major component, and then you purify it. So a lot of our bauxite comes from Puerto Rico. And I think Alcoa has several mines down there, and they just ship it directly to the U.S. Typically they have two possibilities. They can go up the eastern seaboard into the St. Lawrence Seaway, come down to the Great Lakes and access processing facilities there, or they can come up the Mississippi River, up the Ohio River, and end up, past Pittsburgh, and access the Alcoa refineries there. You can also get access to the Tennessee River through the Ohio. Right? Tennessee Valley has some processing there also. But anyway, that doesn't answer the question. What is the question? 65. The Hall process for making aluminum involves what? Chemically reacting alumina with carbon. Well, no. The Hall process, you can do that. React aluminum with carbon. Alumina is the name for this compound. Right? The ore it comes from is bauxite. Alumina is the purified aluminum oxide. Okay, so you can react alumina with carbon and get, but it's very expensive, and it's a messy process. It's difficult to proceed. You know, actually, you get aluminum from reducing that to this. So that means you have to add electrons. Okay, well, actually 3 of them. Now, carbon is involved, but carbon is an electrode that's immersed in something. And that something is molten aluminum oxide and sodium aluminum fluoride, this compound. So Hall just learned that if you want to make a molten aluminum oxide, you need extremely high temperature. I don't remember what it is, but it's very high. And higher the temperature, the more difficult the process. So he mixed this sodium aluminum fluoride together with aluminum oxide, and you grind them really fine. And he found that the melting point was a lot lower for the mixture. So that made it more, it made it easier to produce the molten solution of alumina and this compound. And then you put your electrodes into it. And you put a carbon electrode in one place, and then probably the container served as the other electrode. And you pass electrons through it. And they cause the alumina to convert to aluminum metal. And it sinks to the bottom because it's denser. And then after so much time, you get some brave worker in the proper garb, and they knock the tip off of the reaction vessel, and aluminum metal flows out the bottom. So the answer is C. And the reason Hall did it that way is because adding sodium aluminum fluoride reduced the melting point. But what you need is the free ions, right? In this structure, in the solid, you can't get at the ions. The ions need to be free from one another. And you can either do that in solution, or you can do that in the molten form. In the Hall process, we use the molten aluminum oxide. But there are other reactions, redox reactions, where you can, but you need an aggressive environment to make aluminum oxide soluble. So that's the problem. It's easier to just melt it. All right. Let's see. '68. We're doing good on time. 68. So 68 gives us the starting point, the reactants and the products, and it asks us what's the coefficient of water after you balance the equation. Okay, so we've got manganate ion plus, what's this one? Hydrogen peroxide, H2O2, yields and oxygen. Let's see, this is aqueous and this is a gas. Okay, so we got to tell which one's oxidation, which one's reduction. This one's 0, that one's 2 plus. Remember, oxygen in this one, in hydrogen peroxide, oxygen is -1, not -2. So both of them together are -2, and that makes each one of these hydrogens plus 1. So this individual oxygens are -1. Okay, that's the first trick in doing this one, because there's your oxidation. You're going from -1 to 0. Okay, so that means that's your oxidation. Okay, 0, -1. Your reduction must be this one. So this is -2, -8 total, hold 1 out, +7. Okay. So we have manganate and it becomes Mn2+. Okay. So that makes sense. +7 to 2+, you have to add 5 electrons, correct? So we've got, up here we don't have anything but oxygens and hydrogens, so that step is irrelevant there. But down here we got 1 manganese, 1 manganese, we're good. So let's do the oxygens down here. We need 4 waters, give us 4 oxygens. Now we need 8 hydrogens. And then we have to add electrons too. Right? So we're going to have so many electrons in just a minute. This one, we get electrons on this side. But we've got to balance the oxygens. Well, let's see. There are 2 oxygens here and there are 2 there. So we don't have to do anything. But we do have to balance the hydrogens. Right? 2 hydrogens means there. Now we can do electrons. Right? We've got a +7 to a 2+ means we have to add 5 electrons. And on this one, we're going from -1 to 0 means we only get 1 electron. Right? Just 1. Oh, per oxygen, excuse me. So there are 2. Right? 2 electrons, 1 for each oxygen, -1 to 0. Okay, now we need to make the electrons balance. We've got an even and an odd, so cross multiply is the best action here. We say this one times 5, and this one times 2. Right? So now we have 5 hydrogen peroxide yields 5 oxygens plus 10 hydrogens plus 10 electrons. And here we get 2 manganates plus 16 hydrogens plus 10 electrons, 2 manganese, 2+, and 8 water. There we go. So now the electrons cancel, and we can add everything together. I could cancel some other things here, but I think it'd be easier and more and clearer to put the equations together and then cancel again. So we have 2 manganates plus 5 hydrogen peroxide plus 16 hydrogens that's it. We're doing this one and this one. So we got that one, this one, and that one. Electrons are canceled. Okay, now we come over to this side and we have 2 manganese 2+, then we have 5 oxygens, and then we have 8 water and 10 H+. Okay? So now, the one that we can cancel now are the hydrogens. Right? You got 16 on this side and 10 on that side. So those go away. And now you got 6 left over. There we go. So what's the coefficient of water? Well, we could have answered this question before. Right? The coefficient of water is 8. But I wanted to do the whole thing, all the way to the end. While we're here, what if this reaction were done in basic solution? From this point, we convert it to base. How do you do that? Well, you neutralize those hydrogens with hydroxyls. So we'll say plus 6 hydroxyls and plus 6 hydroxyls. So now this is 6 waters, and these 6 waters cancel and leave us with 2 waters here. So in basic solution, you have 2 MnO4 minuses, you have 5 hydrogen peroxides, you have nothing on this side, no waters, no acid, no hydroxyls. On this side, you have 2 Mn2 plus, 5 oxygens, 6 hydroxyls for the base, and only 2 waters. So the hydroxyls and the waters are on the same side. Okay. That wasn't part of the problem, but I did it anyway. Oh, the next one, 69, says, what's the coefficient of the hydrogen ions? Well, before I messed it up, the coefficient of the hydrogen ions was 6, was it not? Right there. Okay, let's see. 70. Okay, we can do 70. All right, let's see. 70. Oh, this one should be fun. This is a redox reaction that produces pure gold. Au solid. Aha. So how many electrons are transferred during this reaction? Okay, let's write the unbalanced equation first. AuCl4 minus. Notice that this is considered a polyatomic. Right? And then we have copper, solid. So this one's aqueous. Then we have gold. There. And we have chlorine. And we have copper. 2 plus. There we go. Okay. So we know that chlorine is liberated from this polyatomic, but it doesn't change its oxidation state. So it's -1 here. That means -4, hold 1 out for that, plus 3. So plus 3 is going to 0. That's your reduction. Copper is going from 0 to 2 plus. That's your oxidation. So we got copper solid going to copper 2 plus. And then we've got this one with a +3 here going to this one and that one. All right. So we've actually got 4 of those, but that doesn't have any effect on the reduction. This is oxidation. This is reduction. So in order to go, and we don't have any oxygens, right? So we don't have to deal with that. This is going from 0 to 2 plus, which means we've lost 2 electrons for each copper. This one actually adds 3 electrons to go from +3 to 0, right? So how do we balance that? Well, 2 times this one and 3 times that one. So 3 times this one would give us 6 electrons, and 3 times this one would give us 6 electrons. That answers the question. How many electrons are transferred? 6 electrons. Okay. That's as far as you need to go to answer this question.
Call from Kathleen. Call from Kathleen.
All right. Okay. 71. Okay. 71 is another how many electrons are transferred. So let's do this one. 71. I'm going to see if I can show you a shortcut. This one actually is already balanced. Okay, so that one's a 0 oxidation state. This one's a 0. This one's a -1, +1, and a -1. So -2 means +2 there. So we're going from here to here. Let's see, let's confirm. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, 1. So that's balanced. So going from here to here, we actually have a loss of 2 electrons per 10. And from here to here, we have gained an electron per hydrogen times 2, right? 2 equals 2 electrons. So we've transferred 2 electrons. That's it. That's the answer. Okay. This probably should have been E. This one right here. I think it got separated somehow. Not enough info. Well, there's plenty of information. We just answered the question. So that was a shortcut. And the reason it could be a shortcut was that we didn't have to introduce any other components, other elements, other compounds to balance the equation. And in particular, I'm talking about water and hydrogen ions. All right, let's see, 74. How many electrons are transferred in the following reaction when it's balanced in acidic solution? Okay, in this one, we definitely have to separate. We can't just use the shortcut for this one. So we're starting off with sulfite ion plus manganate ion yields sulfate ion plus manganese 2 plus. Okay, let's see. This one is -6 total for that oxygen, so we have to hold out 2. That means +4. This one is -8, hold out 2, -6, +6. Right? This one we've done before, but we're going to do it again. 4 times 2 minus is -8. -7 needs to balance, +7. Okay, so now we know our oxidation numbers. Sulfur is going from +4 to +6. It's oxidized. So we've got SO3, 2 minus, is going to SO4, 2 minus, at +6 and +4. And then reduction is going here. Manganate minus with a +7 for manganese. And that's yielding Mn2 plus. Okay? So 1 manganese, we're good. 1 sulfur, we're good. So now we need to balance oxygens. I'm going to start with this one. 4 oxygens plus 4 water. Now I have 8 hydrogens. On this one, we got a difference of 1 oxygen. So we really only need 1 oxygen over here. Oops, sorry, wrong side. 1 plus 3 is 4, 4. But now we have 2 hydrogens. There we go. Okay, now we can do electrons. So we've got +4, +6. That means we lost 2 electrons total. And here we gained 5 electrons. Now we got to put them together. So that one has to be multiplied by 5 and this one by 2. Okay, so we have 5 SO3 2 minus plus 5 water yields 5 SO4 2 minus plus 10 hydrogens plus 10 electrons. Right. This one we have 2 manganate. Yeah, plus 16 hydrogens plus 10 electrons yields 2 Mn2 plus 8 water. Now, we don't have to add this together, do we? 74, it just says how many electrons are transferred. Ten electrons are transferred. Right? We can add them together. But notice in this particular reaction, you got water on this side and water on that side. So those waters go out and you're left with 3 here. Hydrogens. Well, of course, you get rid of the electrons. Hydrogens, you have 16 here and 10 there. So those 10 go out and you only have 6 left here. So now you just add them together. If we wanted to know the balanced equation, that's what you would do. That was 74. Let's see, here we go. Okay, got 55 minutes left. 74. Oh yeah, we're gonna make it easy. 70. I was looking to see if there was some overlap. '77 and '78 are based upon the same reaction. 76 and '79 are based on the same reaction. Actually, 75. Let's do, those are two different reactions, but they both occur in the dry cell battery, like you would get on the grocer's shelf. All right. Actually, they give balanced equations. So let me just do 70. I'll do 77 and 78. They're the same reaction. So they give us the balanced equation. We got zinc. Let's see. Let me scroll down. 77. There we go. Zinc, 2 manganese oxide. Actually, manganese 4 oxide. And zinc 2 oxide plus, let's see, if this is manganese 4 oxide, this one would be -6 plus 6 plus 3. Manganese 3 oxide. So manganese 4 to 3 means manganese is reduced. We add an electron for each manganese. And this one, zinc, goes from 0 to 2 minus. So that one is, oh, 2 plus, excuse me, 2 plus. That one is oxidized. So what's the question? 77, which is oxidized? All right. Zinc is oxidized. So 77 is A. Zinc is oxidized. How about 78? What atom is reduced? Well, the manganese. Manganese is reduced. Right? It goes from a +4 to a +3. We have to add an electron. Right? That was fairly simple. I noticed notice the difference between 79 and 80. Here we have zinc and ammonium chloride plus MnO2. We're missing ammonium chloride down here. So apparently, these dry cell batteries can have several different recipes to produce their voltages. That's one thing that we didn't dig into. And it's really beyond this class. is actually calculating the voltage that's associated with these reactions. So that's reserved for second semester general chemistry, and it can be done. Right? You can calculate the maximum possible voltage for a particular reaction, and you can calculate the actual voltage based on what the concentrations of your reactants are. You can even calculate the equilibrium constant for the reaction. But like I say, that's beyond this class. Right now, we're just balancing equations. All right, so I'm going to skip that one and go down to well, maybe I won't skip that one. All right, let's do both of them. Let me see. How are we coming toward the end? Yeah, we got time. Let's go ahead and do 79. All right, 79. And this is a balanced equation, right? We can check it out. One zinc, two ammonias. Well, actually, and that hydrogen goes someplace. The hydrogen has to go someplace. So I don't think that's balanced. Two nitrogens, yeah. 8 hydrogens. There are only 6 hydrogens over here. Oh, there's more to the molecule. I mean, more to the reaction. Sorry. We got this one over here. Okay, so that's balanced. So we have zinc plus 2 ammonium chloride plus 2 MnO2, and that yields that, and 2 ammonias plus Mn2O3 plus H2O. Okay. So that's 6, 7, 8. 8 hydrogen. Okay, we're balanced. Okay, what's the oxidizing agent? By definition, remember, the oxidizing agent is that component that causes oxidation. So in order to do that, it has to be reduced. So we need to find out what's reduced. Well, zinc 0 to this compound is oxidized. Right? So it's the reducing agent. So which one is reduced? Well, let's see. This is -1. This is +1. So that means plus 4 minus 1 is +3. This is -3. Yeah. Okay, this is -2, so -4 plus 4. And this one is +3. We did that one earlier. This one is +3, so that's a -3. Right. So the nitrogens didn't change. The zinc changed. Chlorides don't change in this reaction. And oxygen's -2. So the manganese is what's changing. Manganese is going from +4 to +3, which means it is reduced. That makes this one the oxidizing agent, MnO2. There you go. Okay, so we got another, this is a different one over here. 80. 79. Did we do 78 already? Yeah, we did 78 already. So the oxidizing agent in 80, it's a different reaction. Zinc plus 2 MnO2 yields zinc oxide plus Mn2O3. All right, so this is plus 3, just like that one. This is plus 2, and this is plus 4. This is 0. So which one's the oxidizing agent? The one that is reduced. So again, we have MnO2 going from plus 4 to plus 3. Same answer. Different reaction, same oxidizing agent. All right, the last one I have marked is 81. Okay, it's centered. All right, when the equation here in basic solution is balanced using the smallest whole number coefficients, the coefficient of hydroxyl is what? Okay, so we start off with Cl2 yields chloride ion plus ClO3 minus. Okay, this is a special kind of reaction. It's called disproportionation. In other words, it goes two different directions. Right? This one is 0. So it goes from 0 to 1 for that one. And the other chloride ion goes to this one, which is, let's see, minus 2 times 3 is minus 6, minus 5 held out, plus 5. Right? So it goes both to here and to here. So the oxidation reaction is going to be loss of electrons. This one, right? We can't split them up now. I mean, we have to put them together. It's got a whole molecule. And that yields ClO3 minus, which is a plus 5 here and a 0 here. Then the reduction reaction is the same molecule going to chloride. Okay? So, this one says 2, that's 2 chlorines. This one says 2, that's 2. Now, for these oxygens, we got to balance the oxygens. So we say plus, how many 6 oxygens? 6 water. And then hydrogens, we got 12 hydrogens. That's not basic solution yet, is it? This is what I call the fake acid balancing technique. We do the acid first and then we convert it. Okay, now we can do electrons. So if this one's going from 0 to plus 5, that it had to lose 5 electrons each, which means 10 electrons. Okay? For this one, we gained an electron each. But there are 2 chlorines, so we had to gain 2 electrons. Now we need to balance the electrons. This has to be multiplied by 5. So we have 5 chlorines plus 10 electrons yield 10 chlorides. All right, now we can add them together. We get rid of these. Now we can say chlorine plus 6 water plus 5 chlorine molecules yields 2 chlorates plus 10 chlorides plus 12 hydrogens. Okay? Now, that's what it would be in acid solution. But this is base solution. Right? And besides, we can't answer the question yet because there are no hydroxyls there. So we add enough hydroxyls to neutralize this one. Plus 12 hydroxyls. Plus 12 hydroxyls. This makes 12 waters. These 6 waters cancel and leave you with 6 waters on that side. All right, can we reduce it any further? No, that's a unit. That's 1, 5, 12, 2, 10, 6. We can't reduce it any further. So the coefficient of hydroxyl is, well, it says it's 6. And I've got 12. Oh, my mistake. Should be a 5 here. Okay, what did I do wrong? Wait a minute, there's the chlorine. Oh, this is so stupid. I'm ashamed to admit it. We do have 1 chloride from here, but we got 5 from there, which makes 6, right? 6. There, there, there. So 6 chlorides plus 12 yields these. We can divide the whole thing by 2. So if we divide by 2, that's 3, 6, 1, 5, and 3. There you have it. That's why the answer is 6. Okay, that's all I had marked off, and I don't see anything else that just jumps out and grabs me. All right, so are there any questions? Let's see, this is, let's take a look at the syllabus, just to get my bearings again. We've done, let's see, 29th, we finished review on chapter 18, that's the last chapter we're going to cover. Tuesday the 4th of May, that's next Tuesday, will be chapter 18 exams due. And I'll start on that day with a final exam review. And take Tuesday and Thursday to do that. So we can cover all, let's see, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 chapters. So we'll maybe do 6 or 7 chapters one day and the rest the next day. And then you've got till actually the end of exam week. I mean, I put May 13th in there, but that's more or less arbitrary under these circumstances. Okay. Let me stop the share.